Good morning, my dear students. Welcome to the Essay 2, Unit 1, uh, 3 hinged and 2 hinged arches. So, we have completed 3 hinged arches, and now we are in 2 hinged arches. So, last session we have discussed 2 hinged semicircular arch with a concentrated load acting at the crown point. Okay. And in this session we will see how we will solve a two hinged arch applied by UDL on its horizontal span. Okay, so let's proceed for the solution. Now the problem is determine horizontal thrust in a semicircular arch subjected to UDL W per meter run over its horizontal span. So this is a problem given. Right. Let us see how we are able to find just horizontal thrust only. Okay. That is a given problem. Okay. So as we have derived the equation, or you can say a formula for finding horizontal thrust in two hinged arches from the concept of strain energy. Okay, so strain energy concept, you have applied it to the compatibility condition that dou u by dou r is equal to 0. That means a theorem of least work. Okay, that finally led to this equation. Okay, right. We have already discussed how we apply this equation to two hinged arches. This is the second example of using this formula for H to solve two hinged arches. Okay, right. So if you just see the formula, what you need to apply for this solution, H, that is horizontal thrust at springing points, to find which is equal to integral m dash y ds divided by ei divided by integral y square ds by ei. Okay, this is the basic formula that we have derived from the condition of theorem of least work. Now if you want to simplify this equation, you can according to the problem given to you, the ei is constant, so hence we will strike off ei. So what is remaining is simply integral m dash y ds divided by integral y square ds, the simplified formula. Okay, as this is a circular geometry, we need to apply a substitute for all these Cartesian system what is present in the equation. Okay, so we have already noted all these values. So what to apply for y and what is to be substituted for ds and all, and again we will repeat the same. So y here, for a point selected on the arch is this one. This is what is y, and that is equal to the adjacent component of r. So this is r that means the center of the circle, and the point on the arch line joining is nothing but the radius value. So adjacent component is r cos theta. Okay, so this is what we need to substitute for y, and ds is again d theta into r, or else no, you can go for d theta into r. Okay, or r into d theta, whatever it is, right? So these are all no given here. ds is equal to r into d theta, y is r cos theta. Then why you require x here is, no, when you want to write m dash, I have already explained what is m dash. We will just recall it again. So m dash is nothing but the moment in a beam of same span, same load as that of arch. Okay, so now if you draw a beam of same dimension, just draw a beam of same dimension, means what? Span of the beam is now 2 times r. The load is now UDL acting on this total. So it is simply W per meter. Okay. Now this is a case. So there is a section taken at distance x here. The same we consider it here also. Okay. So this is x. Right. Now you write mx, that is equal to m dash. Okay. If you take a beam of same span, same load, instead of arch, and write mx equation at the required point, that is what is m dash. Let us see what is m dash now and how to write it. So the reactions, vertical reactions, if you can work out, total load is nothing but UDL into the span. Span is 2r and load is W. So total load is 2r into W. So as it is symmetric, reactions will be equal, and reaction is equal to half of the total load. Okay. So if you can write that, so that will come to W times capital R. So this is also same as that, W times capital R. So total together 2 times W into R, that is equal to the total load. So sigma Fy is 0 satisfied. Okay. Or else this is by symmetry I wrote it like this. Even if you want to work out what is Va and what is Vb, you may also use the two equilibrium equations, that what you have done uh, regularly for your beams in case of strength of materials that you have solved for support reactions. Okay, so this is from symmetry. Reaction should be same. Va is equal to V, and that is equal to half of the total load. Okay, right. Now you write the moment mx. If you see, so moment from reaction W into R is equal to load into the span. Okay, so what is the reaction W into R, and what is the distance x? So you are writing moments at this section. Okay, so there is a reaction W into R into distance x. WR into x is moment from support reaction. The direction clockwise. So left clockwise, is positive because it is going to create sagging. Okay, so always remember, as we discussed many times, that so if you try bend uh, a stick of, for example, say in this manner, okay, this is sagging. So okay, so left clockwise and right anti-clockwise, left clockwise, right anti-clockwise, both are positive. Okay, so that is what is applied here. Right, now what else you have to the left of this section? You have UDL. Okay, so what is total load? W into the span is x, so W into x, where it will act the center of this x, that means x by 2. So this distance is x by 2. So Wx into x by 2, I write it here in a single step, Wx square by 2. So together it is Wx into x by 2 will become Wx square by 2. So this is how do you write m dash. You have already practiced very much writing mx moment at a section in beams extensively in your strength of materials chapter, right? In that syllabus you have now well practiced with this. So I just to remind you how you write mx from beam. Okay, right now there is a Cartesian coordinate quantity x in this equation. So we already know came to know what to write for other Cartesian coordinates y and ds. So all these are known to you. And now let us say what to write for x. So again the same relation, because it is semicircle. So this is going to be r. So minus this x, sorry, minus this quantity, this quantity will finally give you what is x value. So if you want x, the r minus this quantity, r minus this will give you x. What is that? Is equal to this value, right? This value. What is that? It is opposite component of r. Okay, so what that will become? R sine theta. Okay, so this is r sine theta, opposite component. So r sine theta, r minus r sine theta is x. That is written here. R is taken out, so r into 1 minus sine theta, that is x value. So this is all required for proceeding further into mathematics. Okay, so this is a formula that is to be used, and from that simplified form, as flexural rigidity is assumed as constant, and you finally have simplified equation integral m dash y ds divided by integral y square ds. Okay, and different quantities that you require for proceeding with the solution, they are m dash you require, and y you require, and ds is required. Right, to write m dash again, you need to consider a beam of same span and same load as that of the arch, and work out for mx as you well versed with that from your strength of materials. Okay, how to write mx. And then you come across x, which is another Cartesian coordinate, and how you replace that with polar coordinate system is related here with a simple diagram. Right, these quantities are always required for you if you are working out with a circular geometry. Right. Now let's first simplify m dash or convert m dash into polar coordinate system and then substitute for y and ds to proceed with the integration. Okay. Right. You have m dash wr into x is substituted here, r into 1 minus sine theta. Next, minus w by 2 x square means square of this one. So r square 1 minus sine theta whole square. Right. So what do you get now? It is wr square by 2. Now by simplifying you get, so wr square by 2 cos square theta will be the final form. Okay, you need to simplify a little here. So you have wr square and wr square by 2 term. So you have to no, by 2 if you want, just multiply this with the 2 and divide this entire by 2. So wr square by 2 will come out. So 2 minus 2 sine theta. Okay, all that you have to go for little simplification. Okay, so that will finally lead to cos square theta in the braces. Okay, so here you need to expand this 1 minus sine theta whole square, 1 plus sine square theta. Okay, yeah, something like a minus b whole square. Okay, uh, just a little bit extra line appears sometimes. Okay, right. So right, it is sine square theta minus 2 sine theta. So that is what you have when you expand this one. Okay, so this is how you will end up with m dash value wr square by 2 into cos square theta. Okay, so you need to go for little simplification from this step to arrive at this step. Okay, right, what next? Let's see. So let's work out numerator first, as we always do in case of this h solution. So numerator is simply integral m dash y ds. Okay. Now substitute for m dash what it is, wr square by 2 cos square theta. Just now simplified. Okay, this is m dash value. What is y? R cos theta. What is ds? Is r into d theta. Okay. So now what you have, r square into r power 4 w and divided by 2. This is the constant term which you will take it out from integration. And again, if you see, the given problem is symmetric. Okay, to the left of the crown and to the right of the crown, both the directions, it is symmetric. Load is same, all the properties are same. To the left you have a hinge, to the right you have a hinge. Everything is symmetric. Okay, so that's why what we will do, we will take half of the arch and proceed for integration, and we make that to twice. So what is the half of the arch? Theta 0 to pi by 2. How do you do that? Theta 0 means what? Crown point. Okay, theta 90 means it is springing point. So theta 0 crown point to springing point you are integrating, and the other half is also same. That's why we take this value and multiply it with it twice. Okay, so that is what this 2 meaning. Okay, so 2 times integral 0 to pi by 2. Then what is remaining inside? Then there is cos square theta present and cos theta d theta present. So cos square theta is written 1 minus sine square theta and then cos theta d theta. Okay. So now multiply this cos theta with this. So what you have, cos theta d theta, one integration, and then cos theta into sine square theta d theta, another term. There are two terms here by multiplying with cos theta. Right, so you have 2 and 2 cancelled here. WR power 4 is outside the integration. So what do you do now? Again by substitution. And now when you substitute sine theta is equal to t, then by upon partial differentiation you have dt is equal to sine theta differentiation cos theta d theta. Okay, so this is in place of sine theta, you are able to write t. In place of cos theta d theta, you are able to write dt. Okay, so this first term, what you can replace it here? Integral. What is cos theta d theta? It is simply dt. Okay. How limits will change? How limits will change? So theta 0, sine 0, 0, 0 here. Theta 90, sine 91, 0 to 1. So what this will become? Integral dt means what? T, 0 to 1. So upper limit 1 minus lower limit 0. So what is the value of first term? Is 1. That you can see it here. 1. Right. What about second term? Okay. What is this is about first term, right? Right. Go for the second term. Integral. What is sine square theta? What is sine theta? T. So sine square theta t square. What is cos theta d theta? dt. Okay. Same limits also will change to 0, 1. What is t square dt integration? T cube by 3. This is the integration. Apply limits 0, 1. Right, upper limit, substitute t is equal to 1. 1 cube is 1 by 3. Minus lower limit 0. T is equal to 0. So it is 0. So what is the value? 1 by 3. That is what is it here. 1 by 3. So what is 1 minus 1 by 3? 2 by 3. So 2 by 3 times WR power 4 is the value of numerator. Okay, done? Right. Go for the denominator. As I said, the earlier problem also we have solved on semicircle. So denominator is going to be same. Okay, for all the cases of semicircles. Right? So, but still we will see how we solve for denominator. It's only a repetition. So what is y? R cos theta. So y square r cos theta whole square. What is ds? R d theta. Okay. So r square and r square and r cube will come out. R cube. Okay. 2 times is introduced because of symmetry in the geometry, right? So 2 is already there outside. Right, cos square theta is written 1 plus cos 2 theta by 2. So this 2 and this 2 gets cancelled. So what do you have? Only r cube remaining outside. Right. So what is remaining then? 1 plus cos 2 theta d. So it is what is remaining there? 0 to pi by 2. Okay. 1 plus cos 2 theta into d theta, and outside I mean r cube outside, right? So you have two terms here, 1 into d theta, okay. Right. So 1 into d theta is one term, and cos 2 theta into d theta another term. So 1 into d theta, integral 1 into d theta, what you have, integral d theta, means what, it is theta integration. So apply the limits, 0 pi by 2. That's the first term. Upper limit is pi by 2 minus lower limit is 0. So first term is pi by 2. Okay, this is what is the first term, and that value is pi by 2. What about second term? Cos 2 theta d theta integration sine 2 theta by 2. This one. Limits 0 to pi by 2. So substitute for upper limit, sine 2 times pi by 2 means sine pi. Okay. Sine 2 times pi by 2. 2 theta, right? Theta is pi by 2. So what do you get? Sine pi. Sine 180 is 0. Again sine 0, lower limit. Okay. Sine 0 is also 0. So second term is 0. So finally what you get? Pi r cube by 2, which is same as the earlier problem, which we have discussed in the previous session, right? So now you substitute numerator value. What is that value? 2w r power 4 by 3. This is numerator value. Denominator is again pi r cube by 2. Okay. So what finally you get is 4r by 3 pi into w. Okay. I call this like this. 4r by 3 pi into w means geometry and load I have separated. So 4r by 3 pi, do you remember anything with this 4r by 3 pi? 4r by 3 pi into w is the horizontal reaction value. In case of semicircle applied by UDL on total horizontal span, so 4r by 3 pi into w. What is 4r by 3 pi for a semicircle? Location of centroid is 4r by 3 pi. This is location of centroid. Okay, right? So this is what we have. Y bar we say. I don't know what notation you have used in your engineering mechanics. Centroid location is 4r by 3 pi for a semicircle. Okay, so just to remember this value, that you can write it like this instead of reading it as 4r w by 3 pi. If you read it like 4r by 3 pi into w, means a centroid quantity into the load. Okay, so likewise you can easily remember this value, right? So this is what is the solution for a two-hinged arch applied by UDL on its total horizontal span. The horizontal thrust value is 4r by 3 pi into w, right? Thank you.